Greetings, my name is Daniel Stolfi and I am from the University of Luxembourg. This is a video summary of the research work Optimizing Pheromone Communication in a UAV Swarm. Unmanned aerial vehicles, which are also known as drones, can be multirotors, as quadcopters, or fixed-wing devices, having each class its own advantages and disadvantages. These flying devices are usually equipped with video cameras, radio, and variety of sensors and actuators. UAV main advantages are the ability of exploring different areas, flying at a relatively high speed. These eyes in the sky present also an excellent communication range, as usually there is a clear line of sight between devices. On the other hand, the flying time is short, although it is longer in fixed-wing drones. Our surveillance approach involves the use of multi-swarm of UAVs, which follow unpredictable trajectories. The objectives are maximizing area coverage and spotting all the intruders. We use a mobility model based on pheromones. Additionally, we analyze other two mobility models: CHROM, which present trajectories which are pure chaotic; CACOC, which combines CHROM with virtual pheromones; and our proposal, CACOC+, which customizes CACOC by adding a set of parameters. The use of virtual pheromones is useful to avoid visiting the same spots very frequently and in short time. As pheromones eventually evaporate, those spots are likely to be visited again. If there is no pheromone in the neighborhood, CACOC+ uses CHROM, so trajectories are pure chaotic and unpredictable. On the contrary, the probability of moving towards an area with pheromones is inversely proportional to the amount of pheromones on it. We have proposed three parameters to the original CACOC to adapt it to different scenarios and improve its detection rate and area coverage. They are the amount of pheromone left by each UAV, its radius, and how thick are the trails, and the maximum detection range. But the pheromone maps is not centralized. Although each UAV knows its own pheromone map at any time, radio communications are needed in order to know about the pheromone maps from the other UAVs. Radio links can be subject to interferences. There is a maximum range which also affects the power consumption of the onboard radio device. Using shorter radio packets could improve communications, but could we keep good coverage rate by optimizing the parameters of CACOC+? We propose 4 scenarios to be simulated using the Argos multiphysics robot simulator. Each scenario is made of 100 by 100 cells, and we test 4 neighborhood sizes. The selected optimization algorithm is a genetic algorithm, which is an efficient method for solving high-dimensional problems as ours. We have used binary tournament as selection operator, a uniform crossover operator, a probabilistic mutation adapted to integer numbers, our parameters, and finally, after evaluating the new offspring, the replacement operator selects the fittest individual to replace the worst one in the former population. The problem representation is a vector of integer values, which are the parameters of the UAVs, and the fitness function is calculated as the proportion of explored cells in the surveillance scenario. After performing 30 runs of the genetic algorithm for each scenario and 2, 4, and 6 UAVs, we got the coverage values shown in this table. We also compare our results with CACOC and CHROM. We can see that CACOC+ has improved the other mobility models in all the tested scenarios. The optimization of these parameters allowed CACOC+ to deal with incomplete pheromone maps. We can see that CACOC has problems to cope with communication restrictions. And finally, CHROM has its own limitation since it lacks of pheromones. If you have some questions, here is my contact email. Thank you for your attention.